Welcome to this new video. In this video, we will continue solving this problem that we started in an earlier video. Please, before you continue with this video, go back to the old video discussing this problem. You can find the link to that video down in the description of this video. Now, in that video, we reached this point. So let me just remind you what was the problem. The question says there is a force acting on a particle of mass m, and the force is given by the following relation. Force is equal to a constant called k, that's a positive constant, multiplied by this velocity of the object times the location, the position x. And the question is, what is x as a function of time? There is an initial condition in the problem saying that the particle passes through the origin with a speed v naught or v0 at time t equals 0. So here in the picture, this is the origin, and the particle was here with initial velocity v naught. Now you can imagine, because the velocity is to the positive side, as the object moving to the right, then the velocity will be to the right, its location to the right, that's positive. So this means the force is to the positive side also to the right. So the object will continue moving to the right, and we found in the last video the velocity as a function of x, of location. The result says velocity at any location is equal v0, the initial velocity, plus a constant, and this constant is k divided by 2m, that's the mass, multiplied by the location of the position square, x squared. In that video, we discussed that v0 can never be 0. It should not be 0. In fact, if you think about it physically, if the initial velocity is v0 at the origin, so this means the force is 0 at the origin, and that means the acceleration is 0 at the origin. Now, if the velocity initially is 0 and the acceleration is 0, so the object will never move. So the object will stay all the time at the origin. And that's why we say v0 cannot be 0. This is a physics reasoning for the fact that v0 should not be taken to be 0. We stopped in that video at this point here, and here we want to continue solving the problem. Now the result here, which we found from last time, gives us the velocity as a function of location of x. Now that's a good information, but it's never enough. Now we know that the velocity is changing with x according to this quadratic relation, but we don't know at what time that happens. Like at each position, what time the particle will be there. And so to really understand and to have a good picture of how the object moves, we should find time dependence of the variable x and the variable v, the velocity. So we have to continue solving the problem to understand fully how the object moves. Now to continue, we will try to find x as a function of time by noting that the velocity could be written as derivative of x with respect to time, but we already have velocity, and that's v0 plus k over 2m x squared. I wrote it like this. I saw that what simply I did, I just took v0 as a common factor, so this becomes 1 plus this constant divided by v0 x squared. There is really no physical reason for taking v0 a common factor. It's just simplifying later mathematics. I just took it for mathematical clearness and just to make it easy later in the mathematics. So now I'm going to move this bracket to the other side, divided by, so dx divided by this factor, and this should equal v0, which is still here, and I move dt to that side. Now I will integrate both sides. Now, the integration of the left side is known. That's a really known integration, which is the tan inverse of the square root of this term here. So the answer is tan inverse of the square root of k over 2 mv naught multiplied by the location x, and there's I'm dividing by a constant, the constant with the argument x. Now for physics students at this level, I don't really care about finding out this by yourself. You can just go and consult a handbook in integration, or you can use any software that will give you the answer to this integration. So I know that the integration is a tan inverse multiplying by some constant. So that's the left-hand side. For the right-hand side, the integration is very simple. It's v naught, that constant, multiplied by time, plus a constant of integration. Now, if you think easily about this constant, you can determine that its value is 0. And the reason is because when time is 0, x will be 0. So this term will be 0, and tan inverse will be tan inverse of a 0, which is 0. So 0 will equal to 0 plus this constant, so the constant should be also 0. So now we know the constant of integration. Next, I'm going to move this constant here to the right-hand side, and then get rid of the tan inverse by taking the tan function of both sides, and that will give me x multiplied by this constant equal tan of the right-hand side. I'm going to divide by this constant, take it to the other side to reach the final answer. Please go through these steps carefully, and you can easily reach this result. So this is x as a function of time. It's equal to some constant, tan of some constant multiplied by time. So x is changing with time as the tan of time multiplying by a constant. This is the answer. So mathematically, we found the answer. However, as a physics student, as a student in mathematics, as a student in engineering, as maybe an instructor or teacher teaching this subject, we should never stop at this level. I need to continue and discuss a few things. Probably one of the major things I would like always to stress is, how do you make sure that your answer is perfect, correct? What if I made a mistake during this calculation, and by moving some of these constants to the left, to the right, dividing and so on? What if I missed some of these constants and I got something wrong? So one of the things to check your answer, if it's correct or not, is always very useful to check units or dimensions of the equation. So let's check units. So I have x on this left-hand side, and that's measured in meters. I have this constant now, the square root, and already inside I know the dimension or the unit of each physical quantity. So m is mass, and I know that's in kilogram. V naught is velocity or speed, and that's in meter per second. And I know the unit of k. Now k is the constant that's in the force equation. So you can go back to the force equation and you can check what is the unit of the constant k. Force is in Newton, velocity is in meter per second, and x in meter. So now you can easily find the unit of the constant k. The unit of constant k will be Newton times second divided by meter square. You can simplify this because you already know that Newton is a unit of mass multiplied by acceleration. So it's kilogram times meter over second square. And then by simplifying this further, then the unit of k is just kilogram over meter times second. So now we can check units. Now this square root here should have the units of meters. because you know that tan of this argument shouldn't have any dimension or unit. So the unit of the left-hand side, which is meter, should equal the unit on the right-hand side. So let's check if this square root of 2 multiply the mass multiplied by V naught divided by the constant K should give you the right unit, and that's meter. Now, the unit of this constant is equal to, there's a square root, so that's to the power half here I wrote. Now the number 2 doesn't have units, so just drop it. And remember, we are not checking numbers here, we are only checking units. So mass is in kilogram, velocity V naught is in meter per second, and the constant K is kilogram over meter times second. Simplifying this will easily give you the unit of meter. So that's correct. So we got the correct unit. Now this doesn't prove that our answer is perfect and correct, but at least I know that I'm close to being right, at least. See. Now we can check the tan of the inside, of the argument inside. So let's check this. Well, now the square root of this constant k v naught over t2m should have the unit of 1 over time, so that it cancels the unit of t, and tan will have no units. So let's check the unit of this constant again, k multiplied by v naught over 2m. Now again, easily, there's a square root, so that's to the power half. The unit of k is here, kilogram over meter per second. V naught has the unit of meter over second, and on the denominator I have mass, which is kilogram. And you can easily check that the answer will be 1 over second, and that's correct. So here we check the units. And that's a good thing always to do whenever you get these kind of relations, is to check that you didn't do any mistake. If you got something wrong in the units, then you know that you messed up something and you should go back and check. What is next? I could do also something else, and I think that's a very useful thing to do. And it will help you to understand the physics of the problem. Let's try to check this limiting case. That's k goes to 0. Now what does it mean physically? The constant k goes to 0 becomes so small that the force itself, if you look at the dependence of the force on the constant k, it's linear in k. So as k, this constant, goes to 0, it becomes very small, the force becomes so small. So in the limit that k goes to 0, the force should go to 0. And what does it mean in physics? Well, if the force is approaching 0, then the acceleration should be approaching 0. And that means the velocity should be approaching a constant value. And if the velocity is approaching a constant value, which is the initial velocity, of course, then x should be linear in time. So that x should go as v naught, the velocity, multiplied by t. Now that's from physics consideration. Now let's check mathematics. Now we start with the velocity dependence on x that we found earlier. So if k goes to 0, then that's easily, you can check that this term, the second term, goes to 0, and v is approaching v naught, as we expect. Now, to check the dependence of x, and how x, what does x approach as time goes to 0, we have the relation of x as a function of time. Now, I need to check what is the limit of this expression. Now, to do this, we need to make expansion of the function tan in powers of the constant k. You can go to check this through a handbook of mathematical relations, or you can check series and expansions of functions using any software. By checking any software like Mathematica or Maple or MATLAB or any online free software, we know that the tangent of any argument, alpha, should equal about alpha plus alpha to the power 3 cubed divided by 3 plus etc. Now this expansion is valid for alpha very small is much smaller than 1. Now in our case, we are taking this constant k to be 0. or approaching 0. So this means the argument is approaching 0, is very small, related or in comparison to 1. So we can use this expansion. So the tan, let's take only the first term in the expansion. So tan alpha is approximately alpha. Now by alpha, I mean the argument inside. So the whole argument inside the tan that's substituted for alpha. So the tan or x will approach this constant in the front, it's here, times the argument inside. And that's square root of k v naught over 2m multiplied by t. Now simplifying these constants, you can check that the answer is v naught t as required. So that's another proof that our answer is correct. It is giving us what we expect physically when time, or when k, the constant k, is very small. So that means when the force is very, very tiny. What else to do? Another thing we should always try to do is to plot these functions or these results that we got. For example, x as a function of time goes as a tangent of this argument. So we can plot x as a function of t, and you can do this through any software you have. And we know that the shape of the tan going like this, note that the tangent will blow up at some particular time. Now when time is 0, x will be 0 as expected, and as time changing or going forward, the tangent function will blow up. And when does it blow up? When the argument is pi over 2, because we know that tan of pi over 2 will approach infinity. So this means when the argument inside the tan, when this quantity is approaching pi over 2, the tangent will blow up. And this means when t, I can move this constant to the other side, so this means when time is approaching this value, pi over times the square root of mass divided by 2k v naught. When time is approaching this value, the tangent will blow up and x will blow up. So this means x will go to infinity. And when x goes to infinity, the velocity will also go to infinity. Now what does this mean? It means that as time approaches this finite value, the object will already be very, very far away and having a very huge velocity. Now this is interesting because this tells us only at a finite time the particle will do all these things. It wouldn't take a very long time to do this. Of course, if you know the numbers of this constant, you can substitute and you can find exactly at what time of course, this is the limiting case. So when time is approaching this value, the object will be far away, x will go to infinity, and velocity also will be huge, approaching infinity. So that's a peculiar problem, really. It will only take a finite value of time for the particle to be in the infinity with a huge infinite velocity. We can stop here, or if you want, we can add just one more comment. Now we already know velocity as a function of x, but now I already found x as a function of time, so I can substitute for x, and I can find velocity as a function of time. By substituting the value of x and simplifying, you can find here the result. V is the velocity at any time is equal the initial velocity times bracket 1 plus tan square of the argument square root of k v naught over 2m multiplied by time. There's another way to find velocity also. You can do it through velocity is the derivative of x with respect to time, so you can take the derivative of the position as a function of time, and you can prove that you will get the same answer. Now notice that using the first method, I get this result, which is v naught multiplied by this bracket, 1 plus tan square. using the second method, I know that the derivative of tan is secant square, but now you notice that this bracket before is nothing but the secant square. So the two results are identical, they are the same. And that's a further proof that my answer is correct. So I hope you understand this and you can go through this again. It's very important for a student in physics, in undergraduate university physics, or a graduate, or a student in math, or student in engineering, to be capable of not only finding the solutions, but also to check their solution and to make sure that they understand the meaning of their result. Thank you, and we'll see you in a new video.